So a like we for this question specific is us starting window, and without further ado we do need to actually start rolling. Spells wise, definitely we do actually cast a lot to do with sliding window. Obviously you will also argue brute force to actually counter argue for uh, your spell. For condition, obviously always have the after condition, and then there's a before condition also. So I think the special feature, I just feel the special feature is a lot to do with all these different boxes that actually do happen. So over here, I think there's a operation X that account for your current your sliding window, your current box, and then we have box Y, operation Y, that is actually the rule book that's been established by the Leetcode question itself. And then the Z box, interesting. So the thing is this, your X box has to check with your current window, and then so you are sort of like want to check that is at X according to the rulebook or not, like the rulebook which is Y is a rulebook, so is X equals to Y, but you don't necessarily how say check X with Y. Like you can actually argue, like from previous I also actually do actually talk a lot about this one. So you can actually argue like, why not just check X and Y all together, right? Yeah, you can do that, but the thing is this, you need to run through all the different characters. So if there's like 3 characters for this case, you need to run through the 3 characters each time you want to check whether X is equals to Y or not, right? Because at the end of the day you are checking if X equals to Y, and then you need to go through Y also, basically the same number of like times for this. So there will then be this argument. So this is like operation A per se. So we have the operation B. Operation B is so much more about talking about, you have this separate box. So separate box, which is sort of like a Z value, and the Z at the very get-go will already start to actually establish and say that, okay, how many is like the matching one. So A I got how many, B I got how many, C how many of them do actually match my rule book or not. So at the very start you already say, okay, I got zero, but maybe along the way you do actually find one, so then you will update one. So when you check for that one, you only big O of constant to actually check for that one. So that's the thing about the B operation. So basically what actually happened is that at the start, yes, for the first cycle is that you do check for all 3 of them, but from the second cycle onwards, it's just a big O of 1. You just need to check for the individual item that it actually coincide or not. But for this one, then subsequent the third cycle onwards is also 1. But if you look at A operation per se, is that during the first operation you need to check for everything. Second operation you need to check for everything again, and for third thing third cycle onwards, you need to check for everything again. So like in terms of like time efficiency, A is very inefficient as opposed to B. B will be sort of like a big O of like constant, and then A will most likely be under the time complexity big O of like n per se, where n is the like number of elements in array. So I think that's why you sort of like introduce this z operation is because of like this A and B operation that we actually discussed lah. So then for this part I think this one is the most spot or special feature, but also there's like all these additional facades that's actually going on, is that we want to know what is like the answer key so that we can actually send back to our system. So we have a individual box that say that okay, what is like the current because what we are actually browsing through these boxes is that we are going through an in array. We are going through this array in array, and that for an in array we know the indexes to actually indicate okay at which box are we currently at and how big our box is. So so this one is like maybe say operation W, where we have one box to actually say that okay what is like the start and the end of these in array indexes, and then with that you eventually you can calculate the length of it very intuitively. So that's the additional facade for the additional feature for this question per se. So with that I think that is the very much of the special feature, and I just feel that as this is just a side thing, it's just saying that as we go along that we actually identify that okay we understand how to use our spell already. Very little times or not we do actually need to go inside the inside the question and actually play out to actually start to actually understand on how to actually use our spell, which one is the special feature. Like if we maybe say we at the very go start of like the topic, why not, we won't be able to actually know we won't be able to actually actually identify the special feature right away. But for this question, we're very familiar. That's why the moment we come into this question, we already can identify the special feature without playing it out. Okay, but if we are very unfamiliar, we need to play out, test the water a little bit, and then be able to actually sort of like come up a solution specific. So there's a few things I say that during the play out is that I find very worrisome, something that is like worry. So I think we're gonna actually try to actually go to the play out, talk about it. But before that, I think as we mentioned about this special feature, we do actually accounted for quite a bit of like the rulebook questions, the before conditions per se. So the first item is basically saying that we have a rulebook saying that we need to check for if x is equals to y or not, right? So is x equals to y. So therefore we actually build in, we come up with a higher level of x equals to y by introducing a z box. The z box to actually check for us, which we discussed a lot about the b and a ops, the b and a operation that actually help us to actually solve it. Very interesting. And then one of the other rulebook yeah is a lot to actually the rulebook a lot to do with the white box per se. That means on that we need to fit the criteria of like white box of saying A got how many character lah, B got how many character, C got how many character. And from this while operation, we already can actually see that in while operation, what they actually need is basically some sort of like they need 3 elements. They need 1 element each for each box per se. So yeah. So without further ado, we go into play out series. So in the play out series, at the very start, we do actually say that okay, we start off with like nothing, right? So everything will sort of like be 0 for everything. But the moment you actually step into the A, then you sort of like update that got 1. And actually with that, you establish that you have like the met actually the requirement per se, and then you just update to your Z box saying that okay, I actually have 1 value that's actually inside. So the thing is this, the Z operation will always check that on X got how many fit the criteria is 1, and the criteria to actually until we say we sort of start computing the W operation is that when this Z operation saying that is 3 is equals to 3, then we conduct this W, because it's only then that we have like the answer that we find. So we haven't find answer, haven't reached until the Z operation criteria, so we actually move on. So we come to here, go to A, and then go to D. We don't care. So we don't care is cause that we already established in X that we only am caring about the A, B, C. So if for other elements you show to me and add into the sliding window, add into the box per se, I'm not gonna kind of like affect my system in my X, right? So that's why I don't care. So I add in the B, so update. So this one I care, so I update 1 over here, and it's actually equal to this, so I can update so one thing is this, I don't know how the X operation actually update the Z operation. I don't know how they actually interact, but I do know that the interaction is this, that if X has meets these 3 criteria, then you will update 3, if 2 meet, then update 2. But I don't know how they actually do it. That's the part that I'm very curious, as I was like watching how they actually explain. But I mean, that's fair enough. I really very curious on how they actually am able to do that. Really curious, really. So update to 2 per se, and then we continue, we update, we make our sliding window bigger and bigger as we go along, and then finally we reach until the C, update the C, and obviously we hit the 3 target, so we update the 3 this time round, and we hit this operation. Then we can operate on the operation W right now, saying that, oh, currently this one is index 0 1 2 3 4 5. Oh, this one is 5, so we can update the result sort of like 0 and then the 5, and the length of this will be 6, and then we sort of like store it in our box in for W per se, and then we still got some room for us to play out still, so we're gonna like try to continue. And because the thing is, we want to find the minimum, so that go to our rulebook of saying that we want the minimum length. That's the rule that we want for the minimum of the box to be sent back to our system. Basically, the length to be as little as possible, minimum length, right? So this is like our rulebook that we want to actually establish. That's why we continue in the rulebook. If this is not established, obviously we don't continue lah, and then we just maybe send back this answer if they just need any answer for it. But it's okay. I mean, and obviously you see here is that we have the A, B, and C, because before everything else, I forgot to mention is that the question is basically asking that at which box does the box contain A, B, C, these alphabets. Doesn't matter the order, and that's the question that we are trying to find. Okay, so with that, let's continue. Obviously we want minimum, so we want to actually destroy everything on the set, and then each time that we destroy, we check back with our system with the X and Y, and then go to the Z operation to check. So obviously when we remove the first element, it do affect already. It changes to our 0, it changes the criteria, it changes our Z to become 2, and it doesn't fit the criteria, and then straight away we can't operate the W anymore, right? And the thing about this, later I'm gonna explain for W, which will actually happen very soon. So without further ado, we gonna expand to actually try to find a new box. O doesn't affect, D doesn't affect, E doesn't affect, and now we reach under B. So for this B, we actually do update, but it's not gonna like change anything, because what we cared about is that all 3 of them must actually meet. This thing is over, we don't really care, so we need to wait until A reaches as well before we actually update. So it still cannot proceed to operation W per se. And then we go next, we go A, we found it, and then we update into the 1, and this time round we can update for Z, and it actually met, and that it will update to the W per se. But this time round we see that there's 1, so this is I'll say index 1 2 3 4 5 6 7 8 9 10 1 to 10. Obviously it's like 9 length, obviously doesn't destroy this thing, so therefore we actually go back to actually try to find the answer even more. So we want to find the minimum. Since we actually meet the criteria for this, we can actually proceed to actually try to because of like the rule book of like minimum length, we try to decrease again. Destroy D, and then destroy O. And the thing is this, that we are trying to find the minimum length. So anything that actually defeat this 6, then we sort of like start to actually update this area. But so far here is still like maybe length of 8, length of 7, still not strong enough, so we continue defeat it. We destroy B, we defeat away the B, and it actually do remove and become 1, but it still meet the criteria because all 3 are there, so it doesn't affect our Z, it doesn't affect our W also. And then we count the length as well. Each time we go, we do count the length. So it's index 4 to 10 per se, so that's like 7 still doesn't defeat our 6, so we continue to actually defeat these places. We defeat E, we defeat C per se. Actually we come until here, it's actually 5 to 10. That's 1, 2, 3, 4, 5, and it actually defeat our 6, so this time around we can actually update. So it does update, maybe say index 5 to 10, and that's a length of like 5 per se. 1, 0, 1, 2, 3, 4, 5, 4. Oh no, it doesn't defeat. So come here, try to destroy this C, and we actually in fact destroy this C, and then we doesn't fulfill the criteria again. Go to 2, we can't continue with the W operation. We need to actually continue to find the next valid one. Constantly add, it doesn't affect, and we finally add, it actually does add. It comes to the C, it update the C, and it actually do update this into 3 per se, and it does allows us to actually continue the W operation. But for here, it's at the index 6 to all the way 11, 12, so it's a total of like 7. It doesn't defeat the 6, so we actually continue to actually defeat these places. We defeat, it still doesn't win at all. But right now we are at index 8 to 12 per se. This time around it does actually defeat 8 to 12. So we got 8 to 12, and it actually does defeat to beat this one. So we remove this one, we found a new one, we get greedy, and we continue to actually search more. We actually defeat again, and this time around it's like 9 to 12. We go to the system, we update 9 to 12, a length of 4, and this is actually our final answer. As we actually remove this thing, we don't actually meet the criteria, because it actually become 2 per se at the end, and we can't actually continue anymore because there's nothing else that allows us to move anymore. And we take our breadth system, which is we refer to W, and say that 9, 12, 4, the length of 4 is the highest length with this according indexes. And then we send to the system and we say, yeah, we're done. So I think as we play along, we do actually figure that we use a lot of like the sliding window in the in array per se, and it follow just basically the property of like having the box to actually maneuver around the map per se, to actually help us to actually find the answer. And it actually corresponds with what we actually try to do over here, which is that we want to find the minimum length. So According to the rulebook of having the minimum lag, we always constantly maneuver our boxes to be as small as possible while trying to fit the criteria of having this rulebook of saying that it requires a 3 element, it requires 1 element each, following that rulebook. And as we actually maneuver around our map while obeying the sliding window property. And for this sliding window per se, we are talking about this variable sliding window per se, where our box will constantly adjust based on the rulebook that is actually given to us. And notice how we actually play along with the x and y operation. We constantly adjust, we constantly check that if z meets already, if z meets, then we go to w. If z doesn't meet, we don't care, we continue to actually play with our the maneuvering of the boxes over here. So that's the movements that we are actually getting into per se, as we play along with the x and the y boxes per se. It's pretty fun. We had some fun over here. And obviously with everything else is that you always will have this argument of saying that, okay, why not use the brute force against this sliding window per se. So for brute force, like sure, we can actually find the value per se, but the thing is this, as you see if we go to A, we don't find, and then we finally find a value per se, right? And then what do we do next? We continue plussing like this, because this is brute force. It's kind of like stupid, because the thing is this, we have this rule of like say minimum life, and why the hell are you doing this? It's all redundant move. You're going every single pattern, and the worst case scenario is definitely big O n square, which is very common for brute force. The bad thing about brute force is that you run through every single element, like sort of like ignoring your sort of the rulebook that Leetcode question actually established for you. So it's a lot of like redundant move, I would say. But as opposed to sliding window is like saying that it's like it obeys the rule of like the minimum length. That's why it's so smart, and it's so much more efficient, because it will constantly try to reduce itself the moment so if it's for sliding window, how you will do it instead of this, it won't actually start doing this at all. It won't do these extra moves. It will start reducing this, and then they say, okay, don't have, and then they start to do this, right? It's so smart. You don't do these extra moves, and then you proceed to move much simpler. And I'll say that the time complexity is definitely big O and N for sliding window per se. Easily beat the brute force out of the water. Yep. So with that, very enjoyed my time with this question. Everything comes to an end.